Good afternoon, everyone, and welcome to this talk on serverless design patterns. Before we go into that, I want to go back to what happened in 2014 because quite a lot of interesting things happened. Did you know that in 2014, tacos launched their breakfast menu? I certainly didn't know that until I started looking around. And also, Alibaba had the biggest IPO ever, which is pretty cool. And we also had the Grumpy Cat in 2014. And of course, 2014 was a year when the Frozen came out, so everybody was saying, let it go. And of course, Amazon also announced AWS Lambda at reInvent 2014, and ever since then, I've been able to play this wonderful game where every time I say serverless, somebody reminds me that there's still a server somewhere, which of course is just missing the point entirely. And I love the explanation from Goiko that serverless is serverless in the same way that Wi-Fi is wireless, even though there are still wires hanging around somewhere. When you connect to a Wi-Fi connection, it's just not something you think about. It's not your problem anymore. So serverless is serverless in that exact same way. And what do we actually mean when we say serverless, though? I think after a lot of back and forth in the community, I think we've settled on three properties that any technology is considered serverless if A, we don't pay for it when it's not running, and that we don't need to worry about scaling, provisioning, managing servers themselves, ourselves. Anything that fits this definition should be considered as serverless. And you might have also heard this term function as a service, which is very closely related to the term serverless. And this is where you're going to find the poster boy for serverless, AWS Lambda, but you also find other function as a service solutions, such as Azure Functions, IBM OpenWhisk, and Google Cloud Functions, and so on. And this is a very accurate description of what you actually do as a developer, where I write a piece of function that takes in some invocation event, a context object, and some callback function, and I delegate and I upload it to the cloud provider and delegate to my provider to invoke my function when some event happens in the ecosystem. It could be one of my customers making a call to a HTTP endpoint. It could be someone publishing an event into a Kinesis stream or to an SNS topic, or it could be one of my IoT devices making an update to a IoT topic. When you consider functions as a service, other as a service paradigms, you have infrastructure as a service, you have containers as a service, and you have also platform as a service. And as you can see, functions as a service is closest to platform as a service, the main difference being that your unit of scaling is now the individual functions that makes up the application, not the application itself. And just because something is functional service, it doesn't necessarily mean that it's serverless and vice versa. For example, you may find that the storage services such as S3, it should be considered as serverless by our definition that we don't pay for it when no one's using it, and we don't have to think about scaling and provisioning servers themselves. Same goes to, say, Google Bigquery or Amazon Athena or databases such as Dynamodb. At the same time, there's now more and more solutions out there that allows you to run functions as a service programming model on top of your own Kubernetes cluster or on any form of container cluster. But guess what? When you're not running code on that cluster, you're still paying for it, and you're still having to have someone in your organization to maintain that cluster, manage the scaling, the provisioning, managing the building machine images, and so on. So it's that management of server is still very much your responsibility. So by my definition earlier, I don't consider those solutions as really serverless, quote unquote. That doesn't mean that they're not useful or that they don't have a place in the ecosystem in our tooling, but it just means that when it comes to talking about serverless, what it actually means, I like to make that distinction between what is functional service and what is serverless. And you've listened to people such as Simon Wardley, there's many thought leaders like that. More and more now you are hearing that this idea that serverless is going to fundamentally change how we build businesses around technology, not just how we write code and ship code and run code, but how we build businesses around that. And for good reason too. For one, you have a great scalability out of the box without having to do much yourself. Lambda does have got some scaling limits, and pretty much everything you run in AWS has got limits. But then again, when you consider limits, for Lambda, for example, the most obvious limit is the 1,000 concurrent execution per region per account. That is a soft limit that you can raise. There's a harder limit around how fast you can scale up, which is I think about 500 new containers per minute, which Fine, for some use cases that has got really spiky load, like I have at a zone, that means some use case is not a good fit for Lambda. But to even get to parity with that 500 per minute scaling up limit, you have to do a lot of work. And imagine how much spare capacity you have to be running constantly and paying for to be able to scale 500 new containers per minute in your own cluster. And this whole idea that you don't have to pay for servers when nothing is running means that chances are you can also run your infrastructure much cheaper than the alternative. One typical example would be, how many times have we seen your server running there and we're paying for it 24/7 when all we need to do is use it to run some batch script, say once every hour, maybe sometimes once a day. So that means you are paying for resources that you only use for maybe 0.1% of the time. And with Lambda, with multi-AZ out of the box, so you also get a very good baseline resilience out of the box, again, without you having to do anything yourself. But for me, the most important factor when it comes to the most important benefit of serverless is just that when from having a good idea for a new product feature or a new product to actually being able to run something in production so that I can start to test those ideas against the market. There are just so many things I've got to go through, from deciding what language, what framework I want to use, to capacity planning, setting up the AMI, setting up auto scaling, the ELB, all the rest of it. Whereas with Lambda, when it comes to developing with serverless, a lot of those things becomes either irrelevant or has been drastically simplified. In terms of deployment, I have got so many different deployment frameworks that makes things easy for me, and a lot of capacity planning, setting up ELBs, machine images, and so on. All of those concerns just go away when it comes to using serverless. So in return, I get much greater velocity from having a good idea to be able to start testing the idea against the market, and then most importantly, get rid of the bad ideas really, very quickly and start to iterate on the good ones instead. I get that because I can minimize the amount of undifferentiated heavy lifting that I have to do myself. And I do that, and I also get that because a lot of the operational concerns is now being managed by AWS. A lot of the really hard computer science things and engineering challenges are now being dealt with by AWS, and I can just reap the benefit as a customer. And having worked on several non-trivial serverless applications in the past, one of the things I also started to notice is that this notion of building event-driven architectures has also become far more commonplace nowadays. I think in part thanks to how easy it is to build them with technologies like Kinesis and Lambda. And events become a great enabler for composing different parts of the system together in a way that is loosely coupled. And Lambda is that perfect glue that glues everything together. And I think over time, you also start to see that certain patterns of how people glue different things together start to emerge. And that's the focus of this talk, around some of those patterns that I've been seeing. But as a warning, as it should be customary to any talk that talks about design patterns, I should warn you that design patterns, they're not a recipe for success, because by definition, a pattern is just a repeated way that something is done without any judgment on whether or not that is the good way or bad way, or even if it's the optimal way to do things. And if you're not careful, as the context beneath those best practices and beneath those design patterns start to shift, and you just follow patterns blindly, what you believe to be the best practices today can easily become tomorrow's anti-pattern. Ultimately, there is no silver bullet, and we should stop looking for that altogether. And a design pattern is in no way a substitute for you to really understand the problem domain that you're dealing with and the constraints that you have to work within in your organization. So with that in mind, let's look at some high-level design patterns that people are using for with Lambda, and also some lower-level implementation patterns that we'll go into later. So my name is Yan Cui. I'm a principal engineer at a company called The Zone. We are a sports streaming platform. The easiest way to think about us is with Netflix, where you have a pay-per-month subscription model, but you stream live events, sporting events, instead of movies. And we support over 40 different sports and over 200 different leagues around the world. And recently, we started streaming Serie A and B in Italy and boxing in the US. All in all, We are available in 7 different countries and available on 30 plus different devices. And at peak, we see something like 1 million concurrent viewers on a sporting event. And the interesting thing about our traffic is that everybody comes in about 10 seconds before the event starts. So we have very spiky load because of that. And for that reason, we use a combination of containers and serverless. For the critical path where we see those spikes in traffic, we have to resort to containers because of current limits around the Lambda and also scaling. If you want to find out a bit more about what we do and also look at our openings, we are hiring right now in London, Leeds, Amsterdam, as well as Katowice in Poland. Please go to engineering.thezone.com. And personally, I've been using AWS for about 10 years now, and since July, I'm also one of the community heroes that focuses on serverless side of things. And I've been doing a lot of talks, and then also been putting together a video course with Manning as well, putting together a lot of things I learned through running Lambda in production. And also been doing a lot of blog posts as well. Seriously, I've been writing so much in the last 18 months, which you can find that one link there. So the first pattern I want to look at is nice and easy, is the cron job. This is a perfect example whereby you want to run some code infrequently. So why pay for a server and run it 24/7 when you only need it, say, a fraction of the time? So you can do this by having a CloudWatch event schedule that's triggered to run, say, every 10 minutes, every hour, or whatever frequency you want, and have that trigger a Lambda function. And in this case, we can set it up in CloudWatch events. I can provide a cron expression, and the Lambda function that should get invoked in this case. And following along a similar line of doing operational automation, where everything you write from your Lambda function to standard out gets captured asynchronously and shipped to CloudWatch logs. And that's great, but CloudWatch logs is really bad for searching. For example, I can't search for the same phrase across the logs for all of my different functions. I have to do them for every single function, well, every function's log, which is just not going to scale, right? So what people typically do is they go to the console, they select a log group for a function and say, I'm going to stream the logs for this function to either Amazon's hosted Elasticsearch service, or most likely to a Lambda function, where from there I can just take my logs and ship them to somewhere else. For example, it could be a self-hosted Elk stack, or it could be any one of the number of logging services out there. But what you don't want is to introduce a manual step in the development process whereby someone has to always remember to go to the CloudWatch console and do this for every single new function that they publish. So what you could do is enable CloudTrail, which then allows you to capture API calls made against other AWS services on your behalf. So in this case, whenever you create a new function, the Lambda service itself will call CloudWatch Logs API to create a new log group for that new function. So you can use the CloudWatch events pattern to create a pattern against those API calls that are made against the CloudWatch log service on your behalf, and have that event trigger a Lambda function whose job is to then subscribe this new log group to a Lambda function whose job is to then ship your logs to elsewhere. So this pattern of using CloudTrail to capture API calls in your ecosystem and react to them using CloudWatch events pattern and Lambda is actually a reusable pattern outside of using it to ship your logs to a log aggregation service. So with this particular pattern, you can think of other things. For example, staying with CloudWatch logs, one of the other things that you should think about is, whenever a new log group is created, the default retention policy is to never expire logs. But that doesn't make any sense because I'm shipping my logs to somewhere else already, and I'm paying for storage and usage in that other service. And with CloudWatch logs, they charge you something like, I think, 3 cents per gigabyte per month. So if you never expire any logs, that means your storage cost with CloudWatch logs is just going to grow month on month. So one of the things you could do is apply the same pattern and just automatically update the retention policy whenever a new log group is created. In terms of other things you could do, you can apply the same patterns to. Some of the things I've done in the past include automatically creating CloudWatch alarms against, say, API endpoints latency count, late metrics, as well as the error count metrics, so that every time I publish a new API to API gateway, automatically there's a dashboard that's created for my API, but also automatically I create a set of CloudWatch alarms based on, say, the 95th percentile of individual endpoints or error count for individual endpoints. Other things you could do as well, because with the Cloud Trail, you can capture console login. So if you start to see that, oh, someone is logging into the console from a region where we have no personnel, so something is clearly wrong there, then send yourself an alert when that happens. Equally, we've seen more and more of attackers stealing AWS credentials so that they can spawn up EC2 instances and do Bitcoin mining. So one of the things you could do is using Cloud Trail to monitor EC2 activities. And if you see EC2 activity in regions where you don't have any infrastructure, then that's a sign that something is there's some suspicious activity that you can then create an alert to alert the team to find out what's going on. But then most of us, we're probably not doing DevOps, so we're not doing this ops automation side of things. And many of us are doing web applications using API Gateway and Lambda. And so common pattern would be you've got your single page application, which is served out of S3 through CloudFront, so you get nice CDN caching. And in the backend, you've got API Gateway with Lambda, maybe writing stuff from a Dynamodb table. But then you have Route 53 in front of that, maybe with CloudFront as well. And for implementing authentication, I can use the Cognito as a service, which supports all the usual user flows in terms of registration, verification, sign in, sign out, change passwords, and so on. And it also has got a number of leading practices baked in out of the box, including support for MFA, token-based authentication, capture, and also this, there's no pointer here, but the SRP protocol basically ensures that the password itself is never transmitted over the wire in any shape or form, not even in encrypted form, and only the hash of the password is transmitted and stored on the server side, encrypted. And using Cognito user pool and Cognito federated identities, what I can also do is I can hook up my application, my mobile app, with a number of different OAuth providers, and then using Cognito federated identities, I can authenticate against my OAuth provider, take my token, and then exchange that with the federated identities, who is then going to validate my token, and if it's valid, then I can get back a temporary AWS credential, and from there, my mobile client can directly access other AWS services using those temporary credentials. So these will be the things you do if you want to use the IoT core service, for example, where your client will be directly talking to the IoT service using the temporary credential that it receives from the federated identity pool. Alternatively, if you are using, say, Kinesis to capture BI events, and you want to capture those client-side BI events, like, oh, user have navigated to a different page, for example, then why build an API service in front of the Kinesis just so that you can implement authentication when you can just let Amazon implement authentication for you and have the client talk directly to Kinesis and publish those client-side events. And what about multi-region support? And nowadays, with Dynamodb, you have global tables where you can have the same table replicated across multiple regions. And you also have API Gateway also now supports regional endpoints, which means you can put your own CloudFront distribution in front of those custom domain names you have in the API Gateway, which makes it easy for you to then have the Route 53 route traffic to different regions based on, say, where the user is. And also infrastructure, all of your Lambda functions is talking to different regional tables in the Dynamodb global table setting, so that you get multi-region support, so you get greater redundancy, but also better latency as well for customers from those individual regions. If you want to see how to actually set this up yourself, Alex, who now works for Amazon, has just got a nice video, a webinar, a session that takes you through step by step how to build this yourself. And every business also needs to have a good business intelligence as well. So data lake is also something that now you can easily implement with Lambda and other serverless technologies, such as S3, which is your de facto choice as a data lake in AWS. With S3, you can control access to data in your bucket using IAM, and you can also encrypt them on the server side using KMS with S3 directly. And since the last reInvent, Amazon also introduced a service called Macy, which scans the objects you have in your S3 bucket and notifies you when it detects, say, data that contains sensitive data such as credentials or what looks like AWS credentials, API keys, or maybe PPIs, or personally identifiable information about your customers, so that if you are accidentally writing your customers' I don't know, address or something into your logs that gets put into S3, then Macy can alert you so that you know to go and fix that because of, well, GDPR is now going to affect everybody there. In terms of getting events into S3, most commonly I see people using Kinesis, where they have as a stream whereby all of your different parts of application is publishing events into Kinesis, which then using Firehose, you can pipe all the information from Kinesis into S3 bucket, batched up in, say, 5 minutes worth of data or a couple of megs worth of data, or without having to write any custom code yourself. So all of this can be done through configuration alone or using CloudFront or Terraform, whatever your infrastructure code choice is. And when you have events in Kinesis, you can also react to them with Lambda functions. And when those the events are being aggregated at the Firehose layer, you can also do additional transformation with another Lambda function that reacts to those batches of events in Firehose. And when a file has been dropped into S3 in a batch, you can also then react to those files, again, with Lambda. One use case, or common use cases here is, well, I've got a bunch of events that I'm aggregating with Firehose and putting them into S3, but then I want to, at that point, synchronize with other systems. For example, maybe I want to have a Lambda function, then write the data in a batch and use them to update my Elasticsearch domain, so that if I've got some search as feature in my application, I want to do this because Elasticsearch is not particularly great if you want to update lots of data individually, but it's great for doing a batch update. So potentially this is how you can sync up with different parts of your system. And similarly, if I've got a Dynamodb table that's used to store some transactions, some data, I can also do that as well. In my particular case, I've been also using Google Bigquery a lot for the last couple of years now, whereby when those BI events are aggregated and saved into S3 bucket, I can have a Lambda function live stream those events into Google Bigquery, which has been my BI platform of choice. And of course, since I think 2 years ago, Amazon also announced the Athena service as a direct competition to Google Bigquery, which allows you to write ad hoc queries in almost like SQL syntax against all the BI events that you have stored in the S3. And you can then use QuickSight to then visualize and build dashboards to show those high-level BI metrics such as number of users logged in, number of purchases, and so on, all without having to write any code yourself. Again, all of these are just resources that you can provision within AWS. So you can actually build a fully fledged BI pipeline without almost writing any custom code yourself. All of these things are out of the box and they're all scalable. And the next pattern I want to look at is we talked about this whole idea of building event-driven architectures and how easy it is now to do them with AWS. So we've already touched on Kinesis as real-time stream for capturing those events. And you have in your microservices architecture, you've got different services, or maybe most of them are being built with API Gateway and Lambda, so that everything is serverless. And anytime those systems are creating system updates to the user state, for example, you want to record them as events into your Kinesis stream, so that other parts of the system can react to state changes that are happening elsewhere with Lambda functions. And from there, maybe you want to say, okay, whenever user updates the profile image, I want to publish a update via MQTT to any IoT devices, connect to my IoT topic. And similarly, I want to update my copy, I'm a different microservice. I want to update my copy of the data through a Lambda function reacting to those Kinesis events for events happening elsewhere in the system. And of course, wherever I'm making changes in my microservice, my own boundary context, I also want to record those state changes as events back into my unified Kinesis event stream so that other parts of the system can also react to them. So this is a very nice way for you to build really loosely coupled systems together through events. And hereby, whereby you have many microservices, each one of them is a boundary context, and when one service needs to talk to another to say, hey, I've done something, now it's your turn to do something else, rather than have those services talk to other boundary contexts directly, they should do it through events. And this is not a new pattern. In fact, this has been around for quite a few years now, and you might have known it as unified log processing, even though it's got nothing to do with actually processing logs. But this is the idea is that you have a unified stream that represents all the state changes in your entire system, and different parts, different microservices that makes up that system can all publish events into that stream, or they can also react to events that's happening from that are published by other services. So the interesting thing here is, well, how do you then make sure different services, so service C here depends on events that are being published by service A. How do I make sure that I can discover the contract for those events? Well, this is where things like the Open API spec, which has been extended to support this type of message-driven APIs. And how do I make sure that when I make changes to the events that I'm publishing, that I'm not breaking my downstream systems to make sure that the changes I'm making is backward compatible. And this is where things, the PAC project, the guys working on the PAC project, which is a consumer-driven contracts framework, has also been working on support for this particular use case for serverless applications, whereby you have this nice CLI tool that you can run before you do the deployment to check that the contract that the change that you are making is still compatible with the contract that the consumers for your events is expecting. So I love using events to build systems, but there's one place where I think events is a poor fit, is when you have workflows within the same boundary context, whereby, for example, if I was to implement a order flow for a food ordering service, you can implement that order flow using events. So different parts of the order flows, someone making orders, the restaurant accepting the order, to the customer, the payment being cleared, and so on. Each individual steps can be an event, and you can train up the different Lambda functions that implements the order flow through events alone. But with that, you're kind of taking on the additional overhead in terms of how do you monitor this whole flow? How do you make sure that you can debug things end to end when there's just additional complexity involved there in terms of the end-to-end reporting, also tracking where, say, a particular order didn't complete in time, for example, and since the whole workflow itself doesn't exist as a standalone concept in your application, when someone's trying to understand how the order flow is implemented, you have to look at the different bits that makes up the entire order flow and then mentally construct a picture of what that workflow actually looks like based on your understanding of the individual bits. So what would be a lot nicer is if you can capture the entire order flow itself as one concept, and I can see where this particular order has got to, and see all the traces for all the different steps that has happened on this flow up to this point. And that's where I think using services like AWS Step Function is a much better fit when it comes to implementing some kind of a business workflow. And of course, just because you're using step functions to do the orchestration itself, when your functions are making state changes that other parts of the system may be interested in, you should still record them as events into your unified Kinesis stream. In this case, maybe, okay, a payment has been processed for this user. That is an event that can go into Kinesis so that other parts of the system may be interested in that particular event can react to it. So that's the high-level patterns I want to talk about. There's a couple of implementation-level patterns as well. The first one came straight out of the SOA patterns book. It's called the decoupled invocations. And this particular pattern is good for where you have a business logic that could be quite expensive computationally, or it may just take quite a lot of time because you're working with third-party systems that may be quite slow. And one of the things to keep in mind here when it comes to serverless is that API gateway has got a hard limit of 29 seconds. So even though now your Lambda function can run for 15 minutes on its own, API gateway is going to time out the request after 29 seconds, which means if you have got API endpoints that need to do something that takes longer than 29 seconds, it wouldn't work for you in this case. And also quite useful when you're dealing with downstream systems that are just not as scalable as you are. My Lambda function can scale automatically to X number of thousands of concurrent executions, no problem, without me having to lift a finger. But what if I'm talking to some third party? I don't know if you guys have used Azure or other Salesforce APIs, for example. Those guys just do not scale very well at all. So even if you can scale to whatever you need, those APIs are going to crumble way before that. So In this case, imagine you're dealing with a downstream system that has got some maximum throughput, and you experience a spike, so you're going to pass that entire spike down to your downstream, and they're going to time out, they're going to slow down, they're going to eventually error, and then cause your system to start to error as well. So you kind of just pass the error all the way through back to your user, and that's not great. And as the name of the pattern suggests, we are trying to decouple the reply from the initial request. And in this case, the client might say, okay, API, please do something. And on the API layer, you say, all right, fine. I will accept the request, and I will queue up some background worker to actually do this job. And in the meantime, I'm going to return a 202 with a location for where the result would be once it's ready. So then the client can then regularly ping and say, okay, are we there yet? Are we there yet? Are we there yet? And you just keep waiting. No, we're not there yet, but this is where the result would be, until eventually the background worker has finished his job, informs the API in some shape or form, so the next time the client asks for a result, you can then actually return with a 200 with the actual response the client was looking for in the first place. So this allows you to amortize any spikes in load that you experience passing it onto your downstream system. In this case, if you have a spike, well, I'm just going to do those tasks a bit slower than usual, but I'm not going to pass more load to my downstream system than it's able to handle. And it also means that we can respond to a caller, even if we have to do something that's long and that takes quite a lot of time to process. We can still respond to the client quickly, so that the client can then respond to the user. Think of example would be, okay, we can also be smart about how we represent those progress to the user itself. Take the WhatsApp, for example. Whenever I send a message to my wife, for example, the message goes through several different phases, and it's an asynchronous process. Sometimes it can take a long time before she actually checks her phone. I don't know why she doesn't check her phone more often. And so you can use different representation to show, okay, when the message has its buffer, when it's been sent to the server, when it's been received, and when she's actually read it, when I want to ask her, oh yeah, what are we having for dinner tonight, for example. So by allowing us to decouple the reply or the urgency to reply quickly, and it means that we can now also give ourselves a chance to be more flexible about how do we handle errors, how do we handle retries, so that if, say, the initial request that we're trying to make to the downstream system fails, we can then put an exponential delay. In the case of using API gateway, we are always in the rush against time to respond before the 29 seconds timeout happens. In this case, we give ourselves more room for maneuver. To walk through a simple example, in this case, I've got an API gateway with Lambda function, and whenever I receive a task a request to do some task, I can save the metadata about a task in the Dynamodb table, where the result is null in this case because the result is not ready yet, and I respond to the caller with a 202 and the location header. And at the same time, I'm going to queue up a task in SQS, which is going to trigger a Lambda function to then do the job in the background. Again, my Lambda function can now run for 15 minutes, which means I can have a lot more runway to do this expensive task. And okay, also worth mentioning is that I also have created a timestamp here in the table. This is a mechanism to allow the client to time out the request. Otherwise, you don't want the client to be polling forever. So whenever the client calls my endpoint to check for the result, I'm going to tell, okay, the result is not ready yet, so I'm going to return with another 202 until such a time that the background worker has finished the task and saves the result into the Dynamodb table. So the next time the client calls my endpoint to check for the result, I can see, okay, your job was done. So here's your JSON, or could be JSON, could be something else, your JSON response with a 200 response status code. But this whole thing, since one of the primary drivers for doing this is so that we can amortize any spikes in traffic, and that means that we need to control the amount of concurrency that we have in our function. And one of the ways you could do that with Lambda is if you set the reserve concurrency setting on the function. I know the name reserve concurrency kind of makes you feel that, okay, this is the number of concurrency I'm always going to have. That's not how it works at all. This setting for your Lambda function actually means the maximum amount of concurrency you will have for this particular function. So if you have a reserved concurrency setting of 3, that means at any moment in time, there will only be 3 concurrently executing instances of this particular function. I don't know why AWS decided on to use this name. It's a terrible name, and but unfortunately it's out there, so they can't change it anymore. Another thing you could consider using is using Kinesis streams or Dynamodb streams as well. So instead of having to queue up a task into SQS, therefore creating a transaction, you can also instead just use Dynamodb streams. So by the act of writing to the Dynamodb table, that creates an event. Then I can have a Lambda function react to that event and do the processing instead of having to go through another service as a queue. You could use SNS as well. However, with SNS, the way that the concurrency is controlled between SNS and Lambda is such that every message I publish into SNS topic is going to trigger a Lambda invocation straight away. So it's a one-to-one mapping, and therefore, if one of the purpose of doing this pattern is to control concurrency, then you can't lose the control when using SNS. So one of the things you could do when using SNS is to set the max receive rate per second, but you can only do this on a topic level. When it comes to using Lambda and SNS, you can't just do it on a subscribe level. So moving on to the second last pattern, which is I'm sure everyone's familiar with this already, pops up whereby you have you decouple the broker you decouple the message publisher from the subscriber through some intermediary broker. And then here you have one message that's need to get distributed to many subscribers, and it's good for decoupling the different processing that you have for the same message. And also means that you can also allow for the different subscribers to fail independently without taking down everybody else as well. And in terms of your choice for broker service, it could be SNS, could be Kinesis streams, or it could be Dynamodb streams as well. I think the most popular ones I've seen is using SNS to do this, because one of the things you want here is actually maximize your parallelism and having the one-to-one mapping in terms of concurrency between one message being published and Lambda invocations. This is how you can that's how you can get the maximum amount of concurrent parallelism here. And between Lambda and SNS, you also get 2 retries out of the box. And if you specify a delta Q on the function, then you also get delta Q support out of the box as well. But as we mentioned, since it's one invocation per message, it doesn't mean that you get the maximum parallelism possible, but it also means that you can now have to think about the knock-on effect when it comes to how much load you pass on to your downstream system. Another thing to consider is that you now potentially can suffer from temporary issues that happens in the AWS environment, or potentially if you're dealing with, say, a downstream system that, again, has got a maximum throughput that it can sustain. So if you've got a temporary spike in load, so anything above the maximum throughput is going to error, that's fine, because you get 2 retries out of the box, so you kind of amortize that spike. But what happens if the spike of traffic is sustained for a long period of time? So even your retry is going to fall back into the same period of time, so that the retries themselves can also error, and eventually you're going to exhaust the maximum number of retries you have. And what happens if your downstream system is just having a really bad day, it just experiences an outage? Then any message that gets published in that time when the downstream system is out is not going to get processed. Doesn't matter how many retries you make. So this is where you might want to consider using Kinesis streams instead, whereby whereby the error handling behavior with Kinesis and Lambda is such that it's going to retry continuously with the same batch of records, the previous batch of records, until your function either process them successfully, or until the data is no longer present available in the stream. And with Lambda and Kinesis, you can control concurrency with the number of shards in the stream. So if a stream has got 5 shards, that means the Lambda function that subscribes to that stream at any moment in time, there will only be 5 concurrently executing instances of that particular function, 1 for every shard. So this means that this retry and this success error handling behavior means that you have much better handling for those temporary issues that can happen. And also means that now you can control the concurrency, so that you're not going to put more load to your downstream system than they are able to handle. And in the case of an outage to a downstream system, and Kinesis is just going to keep on retrying, and when your downstream comes back, it's just going to come back and start processing at the maximum throughput that is afforded that's controlled by the number of shards you have in the stream. But of course, you can also use the Dynamodb streams as well. And as opposed to the question of, as to the question of when should you use Kinesis streams versus Dynamodb streams, I think the main question is what is your source of truth? For most of the systems out there, I think the source of truth is what's in the database. But if you're building an event source system whereby then your source of truth could be the events in the stream itself. So as soon as the event is recorded in the stream, that is canon to the state of my system. And you also have considered that with Dynamodb streams, you only get events to a particular table. So if you've got a table that contains, say, user information, then you're only gonna get events about updates to updates to rows in that particular table. And the events themselves are going to describe domain events in Dynamodb. So row inserted, row deleted, row updated. They're not going to describe domain events in your system. What I want to work with when it comes to events is I want to work with user created events. I want to work with user updated events or user sign in, user sign out, whatnot. And using DynamoDBs, I have to mentally map the domain events for DynamoDB and that particular table to what does it mean in my application domain. Operationally, there's also an interesting twist here that the DynamoDB streams actually auto-scales the number of shards based on throughput, which is different from Kinesis. On the one hand, it's great. It means that you don't have to build any custom auto-scaling mechanism for the stream yourself, which I've had to do for Kinesis at a number of places now. But on the other hand, it also means that, okay, now I lose a bit of control in terms of how many shards and therefore how much concurrency I have in my Lambda function. And an interesting difference is that with Kinesis streams, you can extend the default retention policy of 24 hours for data up to, I think, 7 days. With DB streams, you don't have that option right now. And with Kinesis streams, you also pay for the stream for uptime. So you pay for shard hours on top of number of requests. But with DynamoDB streams, you only pay for the number of read requests, which interestingly is free when you're processing events from DynamoDB stream with Lambda, which means when using DynamoDB, you get the stream kind of for free if you want to process events with a Lambda function. And another interesting thing when it comes to understanding the cost of your event source is that I think people don't often think enough is the effect the scale has. If you're talking about having 1 message per second for a whole month and every message being only 1 kilobytes, this is how much it's going to cost you. So straight away you may think, oh, Kinesis is really expensive by comparison to SNS and SQS and other event sources. But by the time you scale up to, say, 1,000 messages a second, the picture looks very, very different now. Now, SNS and SQS can be a lot more expensive because the cost per million requests for SNS and SQS is a lot higher compared to cost of per million requests to the Kinesis. And with Kinesis, you also get a lot of throughput per shard. If you consider that Netflix actually uses Kinesis streams to analyze all VPC flow log, that is, any traffic that's happening in and out of the VPCs are going to Kinesis. And Kinesis is easily one of the most scalable and also probably cheapest service that you can use in AWS at scale. Of course, don't take my projections at face value. They're just estimates. There are loads of other things, variables that can change what how it looks like. Another thing to mention is that you don't have to stop at that one layer of PubSub as well. You can also have PubSub stack on top of other PubSub. In this case, if you want to be able to have a PubSub going to services that is not supported by SNS, you can have a Lambda function also to then react to those events and update other systems as well. The problem to think about here is now you're taking on the responsibility of dealing with partial failures. What happens if a message gets published into SNS and my Lambda function runs and I try to update all these targets, but then 1 or 2 of them fails? What do I do at that point? Do I then retry the whole lot, or do I then only find some mechanism to track which ones failed, so to only retry the ones that failed? So there's one last pattern I want to cover, which is the saga pattern, and it's a pattern for managing failures in a distributed transaction. And it's a pattern that actually dates back all the way back to 1987 in a paper by Hector Garcia Molina. So can Katie McCaffrey did a very good talk on the saga pattern at GoToConf, I think 2016. And she used this example as a distributed transaction whereby you want to book a travel and you need to book your hotel first, then book your flight, and then book your car rental. But what happens if, as part of that transaction, the car rental service couldn't, fail for whatever reason, maybe there's no availability, then, okay, now you need to roll back the whole thing. So you need to apply rollback actions for all the state changes that you have made up to this point. And you can actually model those state updates as well as the rollback actions as Lambda functions. In this case, I have Lambda functions that perform the actual booking, and I also have Lambda functions that model the compensating actions or the rollback actions. And I can use step functions as my coordinator for the entire saga. And in this case, if I want to book a trip to, where am I going, to Dublin, and the happy path, I'm going to book the hotel, that's going to be fine, book the flight, and book my rental, and the booking is done. But what happens if I book my hotel, but then, so for some reason, as part of that booking, something failed. So I just roll back that change that I made so far, and I failed the transaction. But if I make the hotel booking, but then the flight, I couldn't book it for whatever reason, then I have to cancel any changes I made so far for the flight booking, but also then have to process and roll back the booking for the hotel before I fail the transaction. You might notice that there's this recursive arrow here. This is so that if those rollback actions themselves fail, I can just retry for a reasonable number of times before potentially have a different failure path where I alert one of the system, alert someone that the rollback action failed, so we couldn't complete the rollback for this transaction. All the code for that particular demo is available on GitHub, so feel free to check it out. And as I mentioned earlier, I've also been putting together a lot of things I learned about running AWS Lambda in production in the video course for Manning, where we cover all kinds of things from CI/CD, testing, distributed tracing, correlation IDs, and VPCs, and canary deployments, and so on. And right now, you can still get 40% off the course, so we are just finishing off the early access program. And with that, I think I'm just over by a minute or so. Thank you guys very much for your time.